Okay, so today we're going to look at section 6.2, orthogonal projections. Before we jump right into the main topics here, let me remind you of just a regular old projection. So if I have the projection of a vector u onto v, right, so if I have u and v, and I project u onto v, what I get is a perpendicular projection, so a 90-degree angle. This vector is our projection of u onto v. Also remember that this vector here, right, so if I would take the projection of u onto v and I would add it to this piece right here, then I get back to u, which means that this thing right in here, so I got to take this and a plus something, and it makes u, which means that this has to be u minus the projection of u onto v. So that projection plus this, the projections cancel off, leave me with u remaining. So that's the first thing. Also remember our formula. The projection of u onto v was u dot v divided by v dot v, what it's being projected onto, and then in the direction of the vector v, so times the vector v. So this is the stuff we got to remember. What we're going to do today is expand this idea to projecting onto entire subspaces rather than just a single vector. Right, so here's our idea now. Right? Suppose that we had w, which is the span of two vectors now. Let's call it v1 and v2. Let's suppose that these are orthogonal. So v1 and v2 are an orthogonal basis for w. Right, so v1, v2, orthogonal basis for w. Right, so now we're going to think about then w as being a plane spanned by v1 and v2, but these are orthogonal vectors. Right, so let's think about then u, which points somewhere else, right, off of this entire subspace w. So u points somewhere else, and if I want to project u down onto w, the idea is that we're going to actually project u onto v1, and we're going to project u onto v2, and then add up what we get. Right, so our idea here is that the projection of u onto w will be just the sum of the projections onto each of the basis elements. The projection of u onto v1 plus the projection of u onto v2. And the reason that works is because these basis elements are orthogonal. If they weren't orthogonal, when I project down and then add up, we get a parallelogram rather than a rectangle. And it will push it. And since these things are orthogonal down here, when we project down and then add up, we get a rectangle and it pushes it directly underneath where it needs to be. If they weren't orthogonal, when we add up, the parallelogram would push it too far out and it wouldn't work. All right, so this is not special. This really can actually be v1 through vk. I can have any basis elements as long as they are an orthogonal basis, and we're going to come up with the same basic idea. So, for example, so let's look at an example. Suppose that w is the span of the following vectors. These vectors are in fact orthogonal because if I dot them, then I get 0 plus 6 minus 6, which is 0. So the dot product of these two vectors is 0. So these vectors are orthogonal, which means they form an orthogonal basis for w. Let's find the projection of u onto w, where u is the vector 1, 2, minus 1. So again, our idea is that I just need to project u onto each of the basis elements and then add up what I get. All right, so projection of u onto w will be the projection of of u onto v1 plus the projection of u onto v2. Which will be, so if I project u onto v1, let's call this one v1 and this one v2, we're just going to remember our formula, the dot product is u and v1 divided by v1 dot v1 times v1. So that's going to be 1 plus -6 minus 2 over v1 dot itself, 1 plus 9 plus 4, all times v1, plus the projection of u onto v2, which is u dot v2, which is 0 plus 4 minus 3, all over v2 dot itself, which is 0 plus 4 plus 9, all times v2. Well, let's finish this out. This makes 1 minus 8, which is -7 over 14 times v1. And v1 was the vector times the vector v1, which was 1 minus 3, 2, plus 1 over 13 times the vector v2, which was 0, 2, 3. And then we just see what we get. We add these up, and in the end, I'm not even going to worry about putting these into a final single vector, but we get a common denominator, and we put them all together, and we get a single vector, and that vector would be the projection of our starting vector u onto the span of the two basis vectors that we began with, which gave us the subspace W. Let's look at something else. Let's look at another one. We'll practice another one and add something new to the mix. Okay, so suppose that we started with these vectors, -1, 4, 3, 1, 1, 1, -1, 3, -2. Again, notice that these are already orthogonal because if we dot them, we get -1, we get 3, and we get -2, which add to 0. Here's what we'd like to do now. We'd like to write u as the sum of two vectors. We're going to write this as, let's write this as the sum of two vectors, a plus b, where a is in the span of v1, v2, and b, and let's call that w, span of v1 and v2. And let's say that b is in w perp. All right, so we saw w perp before. This is the set of all vectors which are orthogonal to w. So in other words, a is in the span of these two, and b is perpendicular to w. So in terms of a picture, right, so all that we're really doing is what we talked about at the beginning. We've got u here. We're going to write this as the sum of two vectors, one which is in w, and so that will be a, and b will be this one that is perpendicular to w. That's our goal. The idea is the same as before, right? So a is going to be the projection of u onto v1 and v2, which is w. That's a. And b will be just as before, since this is what a is, and when we need to take a plus b, we better get back to u. That means that b is going to be u minus the projection of u onto w. That way, when I add a and b together, I have a positive projection, I have a negative projection, which cancel, and I end up with u back. So a plus b is, in fact, u like we need. And so that's our only real new idea here. We're still at this. Let's practice. We'll practice calculating a and put this all together to see what we get. Okay. So A will be the projection of u onto w, which will be the projection of u onto v1 plus the projection of u onto v2. And just like the last one that we looked at, if I project u onto v1, I'm going to dot these two together and get -1 plus 4 plus 3, all divided by v1 dot itself, which is 1 plus 1 plus 1, all times v1, plus the projection of u1 to v2, dot u1 and v2, and I get 1 plus 12 minus 6, all over v2 dot itself, which is 1 plus 9 plus 4. Okay, all times v2, which is minus 1, 3, minus 2. We need to keep all of our vectors, so let's save them. If I simplify what we have, this becomes 7, 6 over 3, 1, 1, 1, plus 7 over 14, minus 1, 3, minus 2. So that's 6, and that's 1/2. So that's 2, if we push that through. And that's minus 1/2, so 2 minus 1/2 is 3/2. That's 2, and that's plus 3/2. 2 plus 3/2 is 4/2, plus 3/2, which is 7/2. And then we have again a 2, and then minus, so this is 1/2, minus 2/2, which is minus 1, so 2 minus 1 is 1. So that's our vector A. All right. So let's say that A is the vector 3/2, 7/2, 1. And so remember that this is the vector that is in the subspace W. Finally, B, the vector that's perpendicular to W, will be U minus A. Since I need A plus B to be U, that's all we have to do here. So that's minus 1, 4, 3, minus 3/2, 7/2, 1. And what we get is minus 1 minus 3/2. That's minus 2/2 minus 3/2 is minus 5/2. 4 minus 7/2, well, that's 3.5, so that leaves us with 1/2. And 3 minus 1 is 2. And that's our vector B. Now, notice, B was supposed to be perpendicular to W, but W is the span of V1 and V2. So we can be sure that we didn't make any mistakes by taking B and dotting it with these two vectors separately and seeing what we get. So in particular, if I took B dot V1, what we're going to get is minus 5/2 plus 1/2 plus 2. Well, that's minus 4/2, which is negative 2 plus 2, which is 0, which is great. So that means that B is perpendicular to V1. If I took B dot V2, then I'm going to get a positive 5/2 plus 3/2 minus 4. But 5/2 and 3/2 is 8/2, which is 4. 4 minus 4 is also 0. So B is perpendicular to V2, which means I'm pretty confident that we made no mistakes here, because then B is actually, this tells us that B is in W perp. It is perpendicular to W, and we're in good shape. Okay, so couple more things. If we see, I'm not going to work one out like this, but if we see something that says find the closest point in W to the vector U, if that's what the question is, well, the idea is, it's all that we're really looking for is our same picture as before. If this is W and this is U, well, then the closest point is in fact that projection. Right? So really the answer just is going to be the projection of U onto W. It's just another way of phrasing the question. Right? This point down here is the closest point to U that also happens to be inside W. couple other little things. If W is the span of U1 through UK, and each of these things are orthogonal, but also normal, also unit vectors, where U1 through UK is orthonormal. Remember that means that it's an orthogonal set, but each is a unit vector. That word normal here means unit vector. Then we can say a couple of things. First we can remember that the projection of any vector, let's call it a y, onto a unit vector u, so let's call this ui. The point is that the denominator in our projection formula would be ui.ui, but that's the length of ui squared. And so if it's a normal vector, that length is 1. So we actually have a simpler formula. We have y dot ui all multiplied by y. So we don't have the point is that we don't have a denominator if we're dealing with unit vectors. So that's the first thing that's nice. Finally, one last nice thing if we have an orthonormal set that is our basis. So if W is the span of U1 through UK, where these things make an orthonormal set as before, then the projection of any vector y onto the subspace W has a very nice formula. It's U times U transpose, where U is a matrix made by the columns U1 through UK, times the vector y, where U is U1, U2, all the way to UK as a matrix. And so I'm not going to prove this for you. The proof is in the book, if you'd like. It's on page 353 in this section. But we'll look at one example of it, and just so that you can get a feel for how you would use this. It makes for a much simpler calculation than the one that we just looked at. Let's use these values to calculate the projection of y onto W, which is the span of U1 and U2. So let's let W be span of U1, U2, as always, and let's find the projection of y onto W. Now notice that U1 is actually a normal vector. It is a unit vector, because if I take its length, the length of U1 is the square root of 4/9 plus 1/9 plus 4/9, which is the square root of 9/9, which is 1. And the length of U2 is the same thing, because I get 4/9, 4/9, and 1/9. So that's also 1. So both of these vectors are unit vectors. And second, they're perpendicular, because if I dot them, then I get negative 4/3, I get 2/3, and I get 2/3, which makes 0. So this is an orthonormal spanning set for W, which means that if I want to find the projection for y onto W, I'm first going to make the matrix U out of U1 and U2, 2/3, 1/3, 2/3, minus 2/3, 2/3, 1/3. I'm going to look at U transpose, which, remember, really just means take columns and turn them into rows. So this becomes 2/3, 1/3, 2/3 going across, and then this one going across, minus 2/3, 2/3, 1/3. So that's U transpose. Notice now that so this was 481, let's save that. Remember that then the projection of y onto W, according to our formula, is just U times U transpose times y. Notice that this makes sense because u has two columns, so these two have to match up with these two when we multiply. So this is the appropriate order for this to make sense. So what we're going to get is 2/3, 1/3, 2/3, minus 2/3, 2/3, 1/3, multiplied by u transpose, 2/3, that was a third, no, not a half, 1/3, 2/3, multiplied by negative 2/3, 2/3, 1/3, and then all multiplied by the vector y, which is 481. And again, let's just look at this just so that you can see that the dimensions match the way that they're supposed to. If I actually multiply these two matrices together, this is going to make sense. I'm going to get 4/3 and then plus another 4/3. So we actually end up getting 8/3. So this is 4/3 and this is 4/3, so we get 8/3. Next, I'll have 2/3, but not thirds, they're ninths. Ninths. Those are the denominators. Next, I'll have 2/9, and I'll have minus 4/9, which makes minus 2/9. Next, we'll have 4/9 and minus 2/9, which is positive 2/9. When we go to the next row, 2/9 and minus 4/9, which is minus 2/9. 1/9 and 4/9 is 5/9. 2/9 and 2/9 is 4/9. And then finally, 4 and minus 2 makes 2/9. 2 and 2 makes 4/9. And then 4 and 1 makes 5/9. So that's u times u transpose. We need to multiply by 481. Again, notice that the dimensions make sense. Now I have a 3/3, which we got by multiplying u and u transpose, and then we just have to multiply by 481. And so I'm not going to finish this up, but it's just a matter of matrix times a vector, which you can do by hand or you can do with your calculator. And it'll give you a vector in return, and that vector is the projection of y onto the subspace W. I just wanted to point out that the dimensions do match when doing this, and as far as computationally, it's actually an easier thing for a computer to do rather than projecting onto each of the basis elements and adding it up. And so that's what we got for this section. Next time, in 6.4, we're going to see actually where we're going to see the more useful, the next step, which is often what we actually have to do in practice. So what do we have here? We have projection of a vector onto a subspace given by a basis which was orthonormal or orthogonal. Generally speaking, we might not have a basis which is orthogonal, so we're going to have to start with a basis for a subspace which does not necessarily have orthogonal vectors. We're going to have to adjust the vectors so that they become orthogonal, but they still span the same thing. And that's called the Gram-Schmidt process, and so I'll see you for it next time.